Neutrino geophysics is an emerging field that uses neutrinos, tiny, nearly massless particles that rarely interact with matter, to probe the Earth's interior. Unlike seismic waves or electromagnetic signals, which can be absorbed or scattered, neutrinos pass through dense materials like the Earth's core with little resistance. By detecting neutrinos produced from nuclear reactions within the Earth, known as geoneutrinos, or from cosmic rays interacting with the atmosphere, scientists can map the composition and structure of the Earth's layers. For example, geoneutrino detectors have already provided insights into the heat-producing radioactive elements in the mantle, helping to estimate the Earth's internal heat flow. Neutrinos could also reveal hidden geological features such as magma reservoirs or subduction zones, and even detect dense metal deposits. Imagine neutrinos as ghost particles that can travel straight through the Earth, carrying a map of the materials they've passed through. By capturing these particles in massive detectors filled with specialized liquids, researchers can create a three-dimensional image of the Earth's interior, revolutionizing fields like geology, volcanology, and resource exploration. By capturing these particles in massive detectors filled with specialized liquids, researchers can create a three-dimensional image of the Earth's interior, revolutionizing fields like geology, volcanology, and resource exploration.
Neutrino geophysics is an interdisciplinary field that leverages neutrinos, subatomic particles with extremely small mass and no electric charge, to study the Earth's interior. Neutrinos are produced by various sources, such as nuclear reactions in the Earth's mantle, geoneutrinos, cosmic rays interacting with the atmosphere, and nuclear reactors. Their ability to traverse dense matter without significant interaction makes them unique tools for probing regions of the Earth that are inaccessible by traditional methods like seismic waves or electromagnetic imaging. Neutrino detectors, like CAMLAND in Japan, have detected geoneutrinos emitted by the decay of uranium and thorium, providing clues about the radioactive heat production in the Earth's mantle. Neutrinos are like ghostly messengers that pass through solid walls without resistance, delivering information about what lies on the other side. Neutrinos interact with matter only through the weak nuclear force, making them nearly immune to absorption or scattering. This allows them to pass through dense materials like the Earth's core without being significantly deflected. Unlike seismic waves, which are affected by density changes, or electromagnetic waves, which are absorbed by conductive materials, neutrinos provide a direct and unbiased signal of the processes and compositions within the Earth. Neutrinos generated by the Sun pass through the Earth in vast numbers every second, but only a tiny fraction interact with detectors, requiring highly sensitive and massive detection systems. Neutrinos are like beams of light that pass through fog without scattering, providing a clear path of observation. Geoneutrinos are produced by the radioactive decay of elements like uranium, thorium, and potassium in the Earth's mantle and crust. These particles carry information about the distribution and concentration of radioactive materials, which are key contributors to the Earth's internal heat budget. By measuring geoneutrinos, scientists can estimate how much heat the Earth generates from radioactive decay and refine models of mantle convection, plate tectonics, and thermal evolution. CAMLAND and Borexino detectors have measured geoneutrinos, confirming that about half of the Earth's heat flow comes from radioactive decay. Detecting geoneutrinos is like listening to the Earth's internal radio, where the strength of the signal tells us how much fuel is left in the planet's heat engine. For mapping the Earth's interior with neutrinos. Neutrino geophysics enables the creation of 3D maps of the Earth's interior by analyzing the trajectories and energies of detected neutrinos. These maps can reveal the density and composition of layers, such as the crust, mantle, and core. Neutrino tomography, a technique similar to CT scans in medicine, uses neutrino paths to infer structural details and identify hidden features like subduction zones, magma chambers, and mineral deposits. Simulations suggest that future neutrino detectors could map iron concentrations in the Earth's core, offering direct evidence of its composition and dynamics. Neutrino tomography is like using X-rays to see inside the Earth, but instead of light, ghostly neutrinos illuminate the hidden structures. 5. Detecting hidden geological features. Neutrino geophysics holds potential for identifying geological features that are difficult to detect using traditional methods. For instance, variations in geoneutrino flux can indicate the presence of high concentrations of radioactive materials, which might correlate with magma reservoirs or mineral-rich zones. Additionally, neutrino detection can pinpoint subduction zones, where one tectonic plate moves beneath another, offering new insights into plate tectonics and earthquake dynamics. Geoneutrino measurements can help identify magma reservoirs beneath volcanic regions like Yellowstone, aiding in the prediction of volcanic activity. Using neutrinos to detect magma chambers is like finding hidden treasure by following subtle heat signatures. 6. Applications in resource exploration. Neutrino detection can revolutionize resource exploration by identifying dense metal deposits or regions rich in uranium and thorium. Variations in neutrino flux can signal the presence of economically valuable materials deep within the Earth, offering a non-invasive and environmentally friendly method for resource discovery. Neutrino tomography could be used to locate iron-rich regions in the mantle or large uranium deposits in the crust, guiding mining operations. Neutrino-based resource exploration is like a metal detector that works through kilometers of solid rock. Scientific explanation. Neutrino geophysics provides tools for understanding dynamic geological processes such as volcanic activity and earthquakes. Changes in geoneutrino flux near volcanic regions can indicate rising magma or shifts in the mantle, while monitoring subduction zones with neutrinos can reveal stresses building up before earthquakes. This data complements traditional seismic methods, offering a more complete picture of Earth's geodynamics. Example: neutrino measurements around active volcanoes, like Mount Etna, could help track magma movement, improving eruption prediction models. Analogy: neutrino geophysics is like adding a new sensor to monitor the Earth's pulse, detecting early signs of geological stress or activity. Scientific explanation. Despite their promise, detecting neutrinos is extremely challenging because of their weak interactions with matter. Neutrino detectors must be enormous, often placed underground or underwater to shield them from background noise caused by cosmic rays. These detectors use specialized liquids or scintillators to capture the rare interactions between neutrinos and atomic nuclei, requiring precise calibration and massive computational power to analyze the data. Example: the Sudbury Neutrino Observatory and super-Kamiokande use vast tanks to detect neutrino interactions. Future directions in neutrino geophysics. The future lies in developing more sensitive and larger detectors, such as liquid argon time projection chambers or next-generation scintillator detectors, to capture more detailed data. Advances in technology and machine learning will improve neutrino-based imaging. Applications include global mantle mapping, monitoring nuclear reactors, and studying planetary interiors beyond Earth. Example: proposed Hyper-Kamiokande Observatory aims to detect geoneutrinos with unprecedented precision. Analogy: upgrading from a grainy black-and-white photograph to an ultra-high-definition camera for Earth's interior.